Hello, today we shall have tutorial on the mid semester questions, and so this is the tutorial 2. We shall discuss the questions of mid sem exam, and of course, in addition to that, if you have got any other question, we shall discuss. So, first question was, what is channel length modulation effect? How does it affect the characteristics of a MOS transistor? As you know, as the drain voltage is increased, a depletion region is formed adjacent to the drain, and depletion region gradually grows with the increase in drain voltage. So, three different situations are shown. The first one is a non-saturated region, where you can see width of the channel region is changing starting from source to drain, but it is not yet 0 at the drain point. On the other hand, this is the onset of saturation, where you see the pinch off point, it has reached pinch off point, that means the width of the channel region is almost 0 near the drain. But whenever the channel length is small, I mean, then as you further increase the drain voltage, the that pinch off point shifts towards the source. And whenever the device size is large, that means 250 nanometer or 350 nanometer, in such a case, of course, this is not this difference or change is not visible. However, in case of short channel devices, this small change in channel length becomes visible, and it has impact on the drain current. As you know, in the saturation region, the equation for drain current is I d s is equal to k w by 2 L into V g s minus V t whole square. So, in this case, as you can see, there is no equation for drain voltage. However, this length, channel length changes, and since this reduces, the drain current does not remain constant, and as a consequence, what happens, instead of ideally the drain current should have been constant after the saturation point is reached, but it does not remain so. So, it increases. So, this is the effect of channel length modulation, and that means the drain current does not remain constant in the saturation region. Okay. So, as it is shown in this diagram, the variation of drain current due to channel length modulation. Now, coming to the second question, how the transfer characteristics and delay of a static CMOS inverter are affected as the supply voltage is scaled in steps of 1 volt from 5 volt to 2 volt, assuming that VTN is equal to 1.2 volt and VTP is equal to minus 1.3 volt. So, as we know, the CMOS inverters or CMOS gates can work over a over a large voltage range. However, it has impact on the transfer characteristics and delay, and which is shown in this particular example. So, here as you can see, when the supply voltage is 5 volt, so initially when the gate input voltage is less than 1.2 volt, it remains constant, and whenever it is more than 1.2 volt, both the transistors turn on. That means, initially the PMOS transistor is on during this period, and both of them turns on as and as a consequence, the there is flow of drain current, and the voltage goes down, and a point is reached when the supply voltage is equal to 5 minus 1.3 volt. At that point, the PMOS transistor turns off, and as a result the output voltage becomes 0. So, for this region, starting from 1.2 volt to in this case 3.7 volt, there is a variation of the drain current, and of course, this current will be depending on the relative resistance of the PMOS and NMOS transistors. So, this is how it varies. For VDD is equal to 5 volt, and for VDD is equal to 4 volt, similar situation, but when in the input voltage is 0, then of course, output will be 4 volt, and it will remain constant up to input voltage of 1.2 volt. Then again it will start decreasing, and then it will become 0 when the input voltage is 4 volt minus 1.3, that means 2.7. So, at 2.7 it becomes 0, and in this part it changes from 5 volt to 4 volt to 0 volt. So, this is how the characteristic changes, transfer characteristic changes, and similarly for 3 volt, as you can see, more or less it falls very quickly. The reason for that is, both the transistor is remaining on up to 1.2 volt, and then 2 minus 1.3 is close to is 1.7. So, 1.7 volt it becomes 0. So, you can see 1.2 to 1.7 in this range it changes from 3 volt to 0 volt. However, there is a special situation when the we know that when the VDS is less than VTN plus VTP, then we get a kind of hysteresis. So, that is the situation occurs when the drain voltage is 2 volt, and 2 volt is definitely less than 1.2 plus 1.3. So, this is 2.5. So, what happens in this case, as the input voltage increases from 0 volt, the NMOS transistors remains on up to 1.2 volt, then it switches to it turns off, and during this no sorry, I have told wrongly. So, in this part, that PMOS transistor is on for this part. Which part? 2 minus 1.3, that means up to 0.7 volt. So, up to 0.7 volt PMOS transistor is on, and during this part none of the transistors are on. So, the characteristic is somewhat similar to this. Let me draw here. So, up to 0.7 volt, 0.7 volt, the PMOS transistor is on, PMOS on. Then neither PMOS nor NMOS are on up to 1.2 volt. So, during this part none of the transistors are on. So, as a consequence, delay will increase, because the output is remaining VDD, because it had charged to VDD level during this period, but none of the transistors are on. Then of course, the NMOS transistor turns on when it reaches 1.2 volt, and it goes down, the output goes down to 0 volt, and then it remains 0 for the remaining part of the circuit. Now, as you reduce the voltage from VDD towards 0 volt, then what happens, as you go towards this side, the initially the NMOS transistor is on, but NMOS transistor turns off as it reaches the 1.2 volt. So, again during this part, that means input voltage of 0.7 to 1.2, none of the transistors are on, and PMOS transistor turns on here. So, we get a hysteresis like this. That means, as the input changes from 0 to VDD, it goes this way, and if the input changes from VDD to 0, it goes this way. So, if you on an oscilloscope, if you see this, that is known as XY plot, you will see this type of hysteresis. Now, coming to the variation of delay, as you know, the delay is dependent on the supply voltage and threshold voltage. So, the TD, you can say TD is proportional to 1 by VDD into 1 minus VT by VDD. Here I have assumed that both the transistors have the same threshold voltage. However, you have to take into consideration two different threshold voltages for two transistors, and equation will be little different if you have accurate value. But this simple equation you can use to have relative change in the delay for different supply voltage, say 5 volt, 4 volt, 3 volt, 2 volt and 1 volt, 2 volt. So, 5 to 2 volt, 5, 3, 4, 2. So, if we consider the delay corresponding to this is 1, we can find out what will be the delay based on this, because other part is constant. So, here you have got a constant part, that part we can consider same for all the voltages. So, considering the delay is equal to 1 for 5 volt, we can see here delay is 1 for 5 volt is equal to 1. Then how the delay is increasing as you go to 4 volt, it is 1.58. Obviously, it is normalized with respect to the delay of when the VDD is equal to 1 volt, and then you can see for 3 volt it is 2.6, 2.76 times, and when it is 2 volt it is 9.9 times. As you know, when the supply voltage becomes closer to the threshold voltage, then delay increases dramatically, because this part will become very small, and that is what is happening in this part of the circuit. As you can see here, the supply voltage is 2 volt and threshold voltage is 1.2, still it is 0.8 volt difference, and if the supply voltage is further reduced, it will increase very sharply. So, delay will increase very sharply. So, this is how the delay changes for different supply voltages. So, that was the question number 2. Coming to question number 3, an enhancement type NMOS transistor with VTN is equal to 0.6 volt has its source connected to ground and 1.5 volt is applied to the gate, assuming that mu n COX is equal to 100 microampere per volt square, W is equal to 5 micron and L is equal to 1 micron. Find the value of the drain current for VDS is equal to 0.5 volt and VDS is equal to 1 volt. So, when the VDS is equal to 0.5 volt, obviously the transistor is in saturation. On the other hand, when VDS is equal to 1 volt, it is just in when VDS is equal to 0.5 volt, the transistor is in linear region, and when VDS is equal to 1 volt, then the transistor will be in saturation, as it is evident from this relationship. So, I mean VDS is equal to less than VGS minus VT, 1.5 minus 1.2, 1.5 minus 0.6. So, as a consequence, we find that in these two cases the operation of the transistors will be different. That means, the current characteristic will be different. As you know, the current in the linear region is mu n COX by 2 W by L into 2 VGS minus VT into VDS minus VDS square. So, if we substitute it here, that means first equation, that is your I ds linear, that is equal to mu n COX by 2 into W by L into 2 into VGS minus VT into VDS minus VDS square. So, we can substitute different values. Mu n COX value is given, that is equal to 100 into 10 to the power minus 6 by 2 into W by L is equal to 5, and it is 2 VGS minus VT, VGS is equal to 1.5 and VT is equal to as you can see, VGS is equal to 1.5 and threshold voltage is given 0.6. So, 1.5 minus 0.6, it is 0.9, 2 into 0.9 into 0.5 minus 0.5 square. So, if you solve this equation, you will get 0.1625 milliampere. So, in a similar way, you can find out the current in the saturation region. So, in that case, IDS is equal to IDS saturation is equal to mu n COX by 2 W by L and then VGS minus VT whole square. So, in this case, it is 100 by 2 into 5 into VGS minus VT, VGS is equal to 1.5 minus 0.6. So, that will give you 0.2025 milliampere. So, these are the two drain currents in two different regions, linear region and saturation region. That means, in the first case for A, the transistor is in linear region. So, IDS is equal to 0.1625, and in the second case the transistor is in saturation region. So, IDS sat is equal to 0.2025. So, this can be easily obtained as I have shown. Now, coming to the third question, a static CMOS, fourth question, a static CMOS gate is required to provide an output y 1 is equal to a bar B C plus a B bar C plus a B C bar. So, as we know, whenever you are realizing a CMOS circuit, CMOS gate, you have got PMOS network as pull up device, and you have got NMOS network as pull down device, and inputs are applied to both, same inputs are applied, and you take the output from here, and the NMOS network is connected to ground because it acts as a pull down network. This is how realize the function. As you know, this NMOS network corresponds to F bar. So, in this particular case y 1 function you have to realize, and that y 1 is given as a bar B C plus a B bar C plus a B C bar. Now, to find out the NMOS network, you have to complement it. So, you have to get y 1 bar, and that is equal to a bar B C plus a B bar C plus a B C bar. So, this is equal to a plus B bar plus C bar into A bar plus B plus C bar into A bar plus B bar into C. As you know, this we get following the simple rule of Boolean algebra or De Morgan's equation. Now, this network will correspond to this NMOS network. So, which is shown here. You can see the NMOS network corresponds to A, B bar, C bar, which are in parallel, A or B bar or C bar, and A bar or B or C bar, and then A bar, B bar and C. So, this is the NMOS network, and dual of that this can be easily obtained. As you know, the PMOS network is the dual of the this NMOS network. So, wherever it is in parallel, it will be in series. So, A, B bar, C bar, which are in parallel, it will be in series A, B bar, C bar, and it will be PMOS network. Similarly, A bar, B, C bar, we get A bar, B, C bar, which is also will be also in series and in parallel with this. Here it was in series with this, so here it will be in parallel with this. Similarly, A bar, B bar, C, that will be in series, but will be parallel with the other two. So, this is how you get the PMOS network from the NMOS network, the dual of this function. Now, whenever you go for realizing dynamic CMOS, then the network will be somewhat similar to this. So, you will have a PMOS transistor, then NMOS network, and there will be another NMOS network which will be connected to ground, and here will be your primary inputs, and you will apply clock here. So, the NMOS network, if the number of transistors in the NMOS network is 9 in this particular case, n is equal to 9, sorry, number is 9, and so the total number of transistors will be 9 plus 2, that means 11. So, 11 is the number of transistors you require to realize dynamic CMOS. And if you use PMOS network, even then you will have 11 number of transistors. So, this is the question number 4. Coming to question number 5, explain the clock skew problem of dynamic CMOS circuit. How is it overcome using NORA logic? As you know, clock skew problem arises because of delay due to resistance and parasitic capacitances associated with the wire that carry the clock pulse, and this delay is approximately proportional to the square of the length of the wire. When the clock signal reaches a later stage before its preceding stage, the precharge phase of the preceding stage overlaps with the evaluation phase of the later stage, which may lead to premature discharge of the load capacitor and incorrect output evaluation phase. We have already discussed about it. That means, suppose this is the clock of one particular stage, and this is the clock which has reached this is the clock of the preceding succeeding stage, and this is the clock of the succeeding stage. That means, this clock has reached the ith stage earlier than I minus 1th stage. So, as a consequence, when the circuit is in the precharge phase here, it will be in the evaluation phase. So, that will lead to, when it is in the precharge phase during this period, it is in the evaluation phase of the ith stage, and that may lead to as you know, premature discharge of the output, and as a consequence what will happen, it may lead to incorrect output. So, this problem, as you know, can be solved by using NORA logic, where you are feeding the output of a dynamic circuit realized by using NMOS transistors. So, N block, and the output is going to a P block. As you can see, this output will be 1 during precharge, and this will not make any impact on the P block, because PMOS transistors will turn on when the output is 0. Since the output is 1, it will not lead to any premature discharge, and circuit will function without any problem. And so, alternately you will be using N block, P block, N block, and so on. So, NMOS and PMOS transistor networks are alternatively used, and this will overcome the clock skew problem. Now, coming to question 6, obtain an ROBDD for the Boolean function f is equal to 3, 7, 9, 11, 12, 13, 14, 15. These are the min terms of a Boolean function. Now, you have to realize the function using a CPL circuit. So, from this function min terms, you can straight away get a BDD, but obviously it is not minimized. You can see a BDD will have only single terminal, 2 terminal nodes, one for 0 and one for 1. And so, and from this side it is A bar, B bar, dotted lines corresponds to 0, and solid lines correspond to 1. So, you can see this is A bar, B bar, C bar, D bar. So, for A bar, B bar, C bar, D bar means 0, 0 is going to 0. Similarly, A bar, B bar, C bar, D, which is 1, also going to 0, because 0 is 0 and 1, both of them are false in this particular case. So, in this way you can map all the edges to either to 0 or to 1. That means, 0, 1, 2, then 3 is true. So, it will map to 1, then 4, 5 is also false. So, they will go to 0, then 6, 7, 8, these are all false. So, they are coming to 0, and then 9 will go to 1, this is 9, A bar, B, this is your 6, this is I believe this is 7. So, this is A bar, B, C, D. So, A bar, B, C, D, that is 7, that will go to 1, and then 8 will be go to 0, will go to 0, and this is 9, 10, 11 again is going to 1, and 12, 13, 14 all will go to 1. So, in this way you can map all these lines in this manner, and then you can do minimization. So, wherever both 0 line and 1 line is going to 0, or it is going to 1, they are redundant. So, these redundant nodes can be removed, this node will 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 be removed. So, you will be left with this node, this node, this node, and this node, and this node, phone nodes 1, 2, 3 and 4. Remaining 4 nodes are redundant, and directly C will come to 0, Similarly, this C dot will also come to 0 and like that. So, that is what we get in the step 2. Directly C dot is C dot, I mean dashed line, dotted line from C will come to 0. Then similarly, this dotted line from C will come to 0. Then this and then similarly these two, and this will also disappear. So, this dotted line A, B, C. So, 1, 2, 3, 4. Actually, this entire part has been removed, because you can see this will merge and this C will also be redundant. So, this B solid line has come to 1 as it is shown here. So, in this way, in the first step, this much of minimization is possible. Now, we find that for all the D's, dotted line is going to 0 and solid line are going to 1. So, all the D's can be merged together to form a single D, as it is shown in this particular diagram. So, all the D's have been merged, and as you do the merging of all the D's, we find that this C becomes redundant, because dotted line and solid lines are all terminating at D. So, this dotted line from B will come to D, and these two C's can be merged together, because dotted line is going to 0 and solid line is going to D. So, by combining these two C's and removing this C, we get this final ROBDD, because there is, you cannot really I mean minimize it any further. Neither any edge nor any node can be removed from this. So, this is the final ROBDD we get after all these simplifications. So, from this particular ROBDD, which we have got say A, then dotted line is coming to C, solid line is going to B, and you have got a D, and solid line from C is coming here, dotted line from B is coming here, and then you have got 0, dotted line from C will go to 0, dotted line from D is also going to 0, and then you have got 1, and the solid line from B will come to 1 and solid line from D will come to 1. This is the ROBDD that we get. Now, from this you can very easily realize the past transistor network. So, past transistor network can be realized, and which can be used to have the CPL realization. CPL realization you can easily do. Let us consider the realization of this F bar first. So, here it will be, you will be having A bar and A bar, and if we are considering this side, let us consider this side. So, it will go to C, and this will go to C bar, this is C bar, and here you will be having A bar, sorry, this will be, solid line is going to B. So, this will be B, this will be B bar. Let me redraw it separately. So, let us start with A bar, A and A bar, and this side will go to B, B bar, and this side will go to C, and this side will go to C bar. Okay. So, in this case A B, this will be this is going to 1, and as we have seen in this particular case, A B going to 1, and then this will go to D, this will go to D, and this will go to 0, and then your CPL circuit will be having an inverter and a PMOS transistor as pull up device. So, this will be connected here, this will be connected to VDD, and this thing will go to the other side. So, I have to replicate this part, and we shall be having same thing. A bar and B bar and C bar, and again you will be having an inverter, and another PMOS transistor will be here, and this gate will be connected to this, and the gate of this will be connected to other side. So, this is how a CPL realized. Since this is here you are getting F, you will get F bar here, and here you will get F. Now, what will be the inputs here? Since it is realizing the complementary function, only thing that you have to do, you have to apply complementary input. So, here it will be 0, D bar and 1. So, this is how you can realize the CPL circuit starting with this ROBDD. So, this is the ROBDD, and corresponding CPL circuit is shown here. So, this is how you can realize the circuit. So, this is the CPL realization. This is what I have already discussed. Now, coming to question number 7, sketch the schematic diagram of a SRAM memory cell along with sense amplifier and data write circuitry. Explain how read and write operations are performed. So, this is the schematic diagram of a SRAM memory cell. So, you have to explain the read and write circuits, and you can see you have got a memory cell, then you have got row select line and word select line, row or word select line, and column select line is here. So, for write operation, once the column select and row select lines are performed, through the I/O part of the circuit, corresponding bit values will be available there, and once the word line is activated by the row select signal, those zeros and ones, I mean whatever is the coming from the I/O lines will reach these points, and whichever is the 0, that will activate this PMOS transistor. Suppose this is the bit line C bar, I mean if this is 1, that means 0 has to be written. If 0 has to be written, then 0 will pass to this line, and that will make this transistor on, and as this transistor turn on, this will make this line 1, and this will make this transistor turn on, and this will become 1. I mean this will become 0 and this will become 1, because this is turning on and this is turning on. That means T3 is on and T2 is on, that will make this one 1 and this one 0. So, this is how writing will take place, and after you have withdrawn these row select and column select signals, the value will be retained within this SRAM cell as long as power VDD is there. Now, reading operation is little complicated because you have to use the sense amplifier. So, reading operation can be done in 3 steps. First, you have to do precharge and equalization circuit is activated to precharge the bus lines to VDD by 2. So, there is a precharge and evaluation circuit which will be activated to make the bus lines 0. We can draw the circuit. So, initially they will be precharged, both the lines will be precharged to VDD by 2, both the bit lines, that means that bit line and bit line bar. Now, at this point the word line is activated connecting the cell B and B bar lines, connecting the cell to B and B bar lines. As a consequence, a voltage is developed between B and B bar. That means, at this point you are activating the word line. So, this is time. So, at this point word line is activated. So, as the word line is activated, two outputs will have some difference. That difference can range from say 30 millivolt to 500 millivolt, not much. So, So, that much difference will be created between these two buses. That means, if you go back to the original diagram, so a voltage difference will be created between these two lines, that means bit line C and C bar. So, depending on what you are writing, one will become lower than VDD by 2, another will become higher than VDD by 2. So, you will be having a difference of 50 millivolt to 500 millivolt between these lines, and that will be applied to this cross coupled sense amplifier. So, sense amplifier will be activated now, there is a clock, and as the sense amplifier is activated here, this is where sense amplifier activated at this point. So, here exponentially these two will go in two different directions, and very soon it will become 0 and this will become VDD. And here there is a positive feedback, and that is why very quickly this happens. The sense amplifier amplifies the signal and we get a rail to rail output on C and C bar lines. So, this is how in 3 steps this is happening, the read operation is happening. That means, after this is done, you will get here difference between these two lines will be VDD. That means, one of them will be 0 and one of them will be 1, depending on what value was stored in this. If 0 was stored here, that means this will become if 0 was stored, then this bit line C bar will become 1 and this will become 0, and if 1 was stored, this will become VDD and this line will become 0. So, this is what will happen after 3 steps, and I have already explained the write operation, how it occurs. Okay. So, this is how the read and write operation occurs in a static CMOS circuit. Coming to question number 8, a sequence detector produces a 1 for each occurrence of the input sequence 1001 at its input. Draw the state transition diagram of the FSM realizing the sequence detector, and second part is obtain state table from the state transition diagram, and third is realize the FSM using D flip flop and PLA. So, here your question is sequence detector, and that has to detect a sequence 1001. That means, for each occurrence of 1001 it will produce 1. Now, how do you draw the state transition diagram? You have to consider a initial state. Let us assume this is the initial state S1, initial state. Now, either a 0 can appear at the input line or 1 can appear. If 0 appears, then it has to remain in this, because there should not be any change, because no change is required for starting with 0. So, 0 input will produce 0 output. Now, if a 1 appears as input, then it has to switch to another state S2, because it has to detect this sequence. So, a change is required and it will go to state 2 whenever a 1 occurs. Of course, 0 will be outputted at this point. Now, again you have the 2 inputs that can come whenever the machine is in state S2. So, if a 0 comes, what will happen after this, because it is in the proper direction. So, if a 0 comes, then it will go to another state, that is your S3, that means 0 by 0. Now, if whenever it is in this state, and if another 1 comes, then what will happen? That means, if the input is 1 1, then it may be the beginning of another sequence. So, in such a case it has to remain in this state. So, here it will circulate as long as 1 continues to come, but it will keep on producing 0. That means, output will be 0, but as 0 keeps on coming, it will remain in this state S2. Now, the machine is when the machine is in a state S3, 2 things can happen, a 0 can come or 1 can come. So, 1 0 and 0. When a 0 comes, it will go to another state S4. Now, if a 1 comes, what will happen? That 1 that means what will happen 1 0 1, that means 1 0 1 if it comes, then obviously it is not going to produce 1. So, it may, however, this one can be considered as the first one for a valid sequence. So, it will go to S3 whenever a 1 comes producing 0. Now, when the machine is in state 4, now this is now in 1 0, this is 0 by 0 1 0 0 and a 0 has come, and now what can happen, that means 1 it is gone there and 0 it has come here. Now, there is a possibility that either a 0 or 1 will come. Let us assume what happens when 0 comes. If a 0 comes, it has to go back to this point, that means if a 0 comes, then it will go here, that means 0 by 0. Now, what will happen if a 1 comes, where it should go? You see 1 0 0 1. Now, you cannot rule out the possibility of this sequence, that means this can be the end of 1 0 0 1, but beginning of another 1 0 0 1. That is the reason why you have to go to this state. So, it will be 1 by 1. So, this is the state transition diagram for the sequence detector 1 0 0 1. That means, it will have 4 states, and the way the sequence will take place is shown here, and as I have drawn in this diagram. Now, you can very easily obtain the state table from the state transition diagram. So, you have got 4 states S1, S2, S3 and S4. So, 0 0 0 1 1 0 1 1, that is the coding, you have done the state assignment. This step is known as state assignment. It is not necessary that you have to use this code. You could have used say 0 0 0 1 1 1 1 0, you could have given that also. So, here there is no hard and fast rule. In fact, this state assignment plays an important role in deciding the area, delay and power dissipation of the combinational circuit. So, in this case we have done it in an arbitrary manner without considering whether the circuit will be complex or it should have minimum delay, or no consideration has been done. So, with this simple state assignment, you can get the corresponding outputs, that means y 2, y 1 next state values, and the output z, which are for different inputs x is equal to 0 and x is equal to 1, these are listed here. That means, when S1 is machine is in state S1, it will remain in a state S1 when the input is 0, as it is shown here 0 0 to it is going to 0 0. However, if a 1 comes, it has to go to state S2, and so it is going to 0 1. So, in this way you can, when the machine is in state S2, if a 1 comes, it is going to next state, that is state S3, and when a 0 a 1 comes, it remains there 0 1, and when a 0 comes, it has to go to state S3 as it is shown here. Then when it is in S3, it goes to S2 if a 1 comes, S2, and when 0 comes, it goes to S4. So, 1 1 is the corresponding to state S4. Similarly, when the machine is in state 4, it can go to state S1 when a 0 comes, and when a 1 comes, it will give you, it will go to state S2, that is 0 1 is the code for that, and however, here it will produce 1. So, from this you can very easily write down the equation for y 2, y 1 and z. So, y 2 and z is true only here. So, z will be equal to y 2 y 1 x, x is equal to 1, y 2 is equal to 1 and y 1 is equal to 1. And you can see y 1 is, this is y 2 and this is y 1. So, y 1 will be equal to, in this case it is x. That means, when x is equal to 1, I mean for all the state combinations, it will go to y 1. So, y 1 is equal to x plus corresponding to this, that is your y2 y1 bar, x plus y2 y1 bar will be the expression for y1, and expression for y2 will be corresponding to these two, that means y2 bar y1 x bar plus y2 y1 bar x bar, and which has been written here. So, this is z x y2 y1, y1 is equal to x plus x bar y2 y1 bar, and y2 is equal to x bar y2 y1 bar plus y2 bar y1, as I have shown from this table. So, from this table straight away we will get this, and then you can realize the PLA corresponding to this particular expression. As I have told, it will have 4 how many product terms? You will have one product term x bar y2 y1 bar, another product term x1 bar y2 bar y1, 2 product terms, third product term is x, fourth this product term is common here already, x2 x bar y2 y1 bar, it is already there. So, 1 2 3 and then 4 x2 x y2 and y1 bar. So, there will be 4 product terms, and for these 4 product terms you will have a you will have 4 lines, these lines correspond to each product term. So, you have got 1 2 3 and 4. For 4 product terms you have got 4 lines in the PLA, these are the row lines, and then it is non-NOR PLA. Here I have applied the 4 inputs x y1 y 3 inputs x y2 and y1, x y2 and y1 which are complemented, outputs are also there, and this particular row corresponds to the product term x bar y1 y2 y1 and y2 y1 bar and y2. So, this row corresponds to that, and this row corresponds to the other product term x bar y2 y1 bar, this row corresponds to x, this row corresponds to x y2 y1. So, this is how you can realize y2 y1 and z, and y2 and y1 these are the next state functions, they have to feed them to D flip flops and then feed back to the that will generate y2 and y1 after a bit delay, and this is how you can realize the complete sequential circuit using PLA. So, PLA is realizing the combinational part of the circuit, and these two are the D flip flops that is required to store the states of the machine. That means, those 0 0 0 1 0 2 0 1 1 0 1 1 will be stored here, and that will give you the states. So, with this we have discussed all the questions that was set in the mid semester exam. Now, if you have any other question, you can pass on the papers, write it on a piece of paper and pass on to me. Write your questions on a piece of paper, pass it on to me. So, 5 minutes left, I can discuss 1 or 2 questions if you have any, otherwise you can end this session. Okay, thank you. We are ending this tutorial 2 session. Thank you very much.